Let's play a card game. I've got all the 13 card values listed above on this piece of paper, and I'm going to make sure my cards are shuffled really well. When I get done shuffling, I'm going to begin to split the deck into 13 different piles that each have 4 cards in them like so. And what the game is using each pile exactly one time, is it possible for me to pick a card with each value. When I get done with a pile, I'm going to turn it over so I don't reuse it again. So this is kind of like solitaire in a way, where as I decrease the number of piles, I have less options for how I'm going to match that value of the card. So I'm creating maybe some opportunities that I might get stuck and therefore lose this game. The way I'm playing right now, I don't have a particular pattern in mind. I've got 3 piles left, but you see with these last 2 piles, I can't make the matches. Now, is there a different sequence of choices I could have made that would have allowed me to win? Or did I just get unlucky with the shuffle so that this arrangement of piles was just unwinnable? The answer to this question can be found using a branch of mathematics called graph theory. A graph consists of vertices and edges. Here's an example. We're going to draw some dots. You can draw as many as you want in whatever pattern you want. We're going to call these the vertices. The edges are just going to be any lines between vertices. A bipartite graph can be split into 2 sets of vertices we'll call A and B, such that there may be edges between A and B, but no edges within A or B. So in a picture here, I'm saying that if I've got these 2 sets of vertices, I can have edges between them, but I can't go red to red or blue to blue. Now we can represent our card game as a bipartite graph. One set of vertices should be the card values, and the other set of vertices should be the piles, and we'll draw an edge between vertices if that card value is in that pile. Notice that each pile has at most 4 distinct card values. We'll say a bipartite graph has a matching if it's possible to use some of the given edges to pair each vertex in A with a unique vertex in B. So if we use the bipartite graph we saw earlier, we'll use these yellow edges here to visualize a matching in this bipartite graph. So winning our card game corresponds to finding a matching in the related graph. For the graph I drew earlier, this arrangement does have a matching that I found here and colored it in yellow. Therefore, asking if our card game is always winnable is equivalent to asking if all such graphs have a matching. We'll see that the answer to this question about abstract graph theory, and thus to our question about our concrete card game, is yes. Let X be any handful of vertices from A. The neighbors of X are the vertices from B that connect to the vertices in X. The neighbors of X are going to be denoted by N of X. Let's look at an example with a bipartite graph from earlier. So what if I just pick 2 vertices on my set X? Then I'm going to follow the edges to the corresponding B vertices, and those are going to be the neighbors. Now what does this have to do with matchings? The answer is Hall's marriage theorem. Here's a version of it. Let A and B be 2 vertex sets for a bipartite graph and assume they have the same size. Then the graph has a matching if and only if any handful of vertices from A has at least that many neighbors in B. In symbols, we're saying a graph has a matching if and only if for all subsets X of A, the size of A is at most the size of the neighbors. And for us, our card game is always winnable if and only if for any handful of different card values you pick, there are at least as many piles that have those values. So for example, if we pick 2 card values, say 2 and ace, then there must be at least 2 piles that have those 8 cards. To see this, otherwise, that would mean a single pile has all 8 of those cards, which is impossible since a single pile has 4 cards. What we're going to do is generalize that idea to a proof. So how would this go? In general, say we pick m different card values. By way of contradiction, suppose there are fewer than m piles that contain all these values. In symbols, let's say that there are n of these piles, but n is less than m. Then the total number of cards in these piles should be 4 times n. We've supposed that our 4 times m cards are in these piles. But that means 4 times m is less than 4 times n. And if you divide, that says m is less than n, and that contradicts that n is less than m. Thus, for any m different card values we pick, there must be at least m piles that have these values. We can model this game in Python and use the networksx package in order to visualize the bipartite graph and also to find a matching. In other words, we can use Python to help win this game. So if you follow along, I created a blank graph. I'm going to add the card values as one set of nodes in my bipartite graph. And then what I'm going to do is I'm going to make a list of each of the piles. And I put the values that are in each pile here. Now that's a list of lists, and just for convenience, I need those to be strings, so I'm going to convert those to strings. So I'm going to add the piles as my other set of vertices in my bipartite graph. And now what I want to do is make the edges. And so I just have this for loop that says, hey, if that value's in that pile, make an edge between those. We can use matplotlib in order to draw this bipartite graph a little bit later. Now I also want to use the built-in function of finding a maximum matching that's part of network X. And so that little snip right there will find a matching between my card values and piles. And I would like to visualize what that matching looks like, so I made this new graph, g_max, and I want to plot that too. Now I made a little mistake that I needed to fix here as far as underscores versus dots, but here are my two bipartite graphs. On the left you see just what the game looks like, and on the right would be the way to win.